Okay, so this video is a little bit late because of the exam and everything, but I am putting it out today. So this week we're covering chapter 7 on space and time trade-offs. So the idea here is that we can do some input enhancements. We can do some things beforehand that take up more space on some storage device, but yet allow for a quicker time to process it, okay? So there are a couple of the examples here that we'll talk about. We also call this pre-structuring. It's a way to organize the data, okay? So there's more of this kind of information in the chapter on dynamic programming, which is chapter 8, which we're not going to cover, okay? But if you want to look at it, you certainly can, okay? So the first one here in chapter 7, section 7.1 is sorting by counting. So it's the idea that if you can go through and for each element of the list, figure out how many elements are smaller than that element, put that in a table, okay? The table will then be able to determine the positions in the sorted list, right? Okay, so for example, if the count is 10, as the book gives us here, it should be in the 11th position, meaning because if there's a 10 there, it means that there are 10 numbers smaller than it, so it must be in the 11th position, okay? And here's an algorithm on how to do this. Okay, I think that's relatively straightforward. There's an example there as well. Okay. And then the next section here talks about this distribution values. And I think just focus on the first part and you should be okay. Okay, we won't worry about the distribution ones. I want to keep it relatively straightforward. Okay. The next section is talking about string matching. So we've done the string matching before, where we're just doing a brute force algorithm that if we have the pattern we're looking for in the text, we move it over one every time until we find it, okay? And if we find a match on the first character of the pattern, we go to the second and the third and so forth, okay? Well, there are some efficiencies that we can do there, okay? Because if, for example, the second element isn't correct, we know we can stop, okay? And if the pattern doesn't contain anything there, we'll be able to get more efficient, okay? So that's certainly something we can look at through some of these algorithms. Okay, so let's take a look at the. Okay, sorry, I had to pause there. My dog was barking at me. Okay, so again, we're going to go through and look for some cases where we can get some efficiency over the brute force. Okay, so a couple of algorithms here that have been developed that do this. The one we're going to talk about is the Boyer-Moore algorithm. Okay, so it's relatively straightforward. So it starts here with this idea of Horseball's algorithm. Okay, so it's a simpler version than the Boyer-Moore, and therefore it tends to be a little easier to understand what's going on here. Okay, so here's an example. If we're searching for the pattern barber, okay, and I'm right here in the text, we're looking for barber in some bigger text. The text is going to go from S0 up to S of n minus 1. Okay, if we start with the last R patterns, okay, last R of the pattern here. Okay, and we're moving left to right. We're going to compare the corresponding pairs of characters in the pattern in the text. Okay, if all of the pattern's characters match successfully, then we're done, right? But if not, okay, we then can shift the pattern to the right. We want to shift it as far as we can to the right. Okay. To make it go quicker, okay? In a brute force, we're doing it one at a time. So we want to be able to shift it to a bigger thing, okay? So we're looking here, for example, okay, we're at some position in, and I'm right here in the case 1, just to show what we're talking about here. Okay, so we've tried to place barber somewhere into our pattern. We're looking at this last character, and we see that it's not a match, okay? So when that's the case, there are 3 conditions we can meet. Okay, so we're going to call this position C from up here. Okay, so case 1, if the pattern that we have, so we have an S here. Okay, if there are no S's in our pattern, okay, so barber has no S's, so that's the case now. Okay, we know that by moving this over, this can't be in any of the positions. Okay, so moving the brute force would have us check it for here, here, here. It's not going to be any of those. Okay, so it's easy enough to check that because the pattern's smaller. Okay, so if it's the case that there are no C's in the pattern at all, we can move the whole thing to the next pattern. Okay, So in an unsuccessful search, if it's set up correctly, you can jump the whole pattern every time. Now, of course, you may have some false readings there, okay? So again, because S doesn't appear in Barber, I know that S cannot be any of those positions. I can start searching one to the right of that, okay? So again, this pattern searching starts from the left, but it starts at the right end of the pattern, okay, rather than the left, okay? So case 2 here, okay, is that there are occurrences of C in the pattern, okay, but they're not the last one, okay? So in this case, down here a little bit, we search for the position at C is a B, okay, and we're comparing it against the one here, okay? So it's not the end, so we don't have to worry about checking anymore. We know it's not going to fit, but we can move that over to line up this B, okay? When you move that over and line up this B with that B, okay, you can then match. I mean, we see this doesn't match either because these don't match, but you can then move on and do another search. Okay, so you're moving over by however far you can till you get to that first letter. Okay, so our case 3 here is C happens to be the last character in the pattern. Okay, but there are no C's among the other characters. Okay, so in this case, we find an R, okay? So we go down and see that there's an R there, and then the E matches up. But then we finally get an M, and there are no M's in the rest of the pattern. So at this point, we know that all of this is wrong. These two can't be right because that's not right. So at that point, we can shift all the way over past the end of C to C+1, okay? So the final case here is that if C happens to be the last character in the pattern and there are no other C's among the other characters, okay? It's similar to case 2. So in this case, we look at the R's match up, life's good, but you get over to the next character and they don't match, okay? So we're at this last R, okay? But there are other R's here, okay? So I said there are not, but so again, this is C happens to be the last character, but there are other C's among the characters, okay? So there's another R here, okay? So our next step would be to move it so that this R lines up to see if that works, okay? So those are the 4 cases that we have to worry about, okay? Of course, the case it could just match and then we're good, okay? But that should allow us to leap forward sometimes, okay? So here is going to be where we're going to go through based on the pattern, okay? And we're going to output a table of all possible alphabets, so we can have all possible characters in the alphabet, so we don't have to calculate that every time, okay? So here's the pseudocode for the shift table, and then it's just going to go. It's going to fill the table by looking for a character in the pattern, and then that's it, okay? So we can now look at the Horseball algorithm being the step 1, okay, for a given pattern of length M, and the alphabet used in both the pattern and the text, so all the characters that are there. We're going to construct the shift table, as we just described in that pseudocode. We're then going to align the pattern against the beginning of the text, and then we're going to repeat until we either find a matching substring or it reaches beyond the last character of the text, okay? So starting with the last character in the pattern. So again, we align the pattern to the left, we look at the character to the right in that pattern, okay? We're going to compare the characters in the pattern in text until either all M characters are matched, and we stop and we're done, or a mismatching pair is encountered, okay? In the last case there, we're going to retrieve the entry from the shift table, okay, from the C's column of the shift table, where C is in the text character currently aligned against the last character, and that will tell us how far we have to move without having to calculate that every time, okay? So in essence, it's the part in the cases here, the calculating how C compares to the rest of the pattern. That's what we're doing with the shift table, okay? Okay, so then here becomes the whole algorithm in pseudocode for the string matching, okay, where we're inputting a pattern P and a text, okay? Again, we're searching for the pattern inside of the text, okay? we're starting by calling the above algorithm to create our shift table. Okay, we're then going to position the pattern. It's the position the pattern's right end there. Okay, so it's how big the pattern is, starting with the 0th position. Then we're going to go through here and keep doing this. Okay, so here's an example of this where we're going through the Horseball's algorithm. Okay, we're looking for barber in the text that has English letters and spaces. Okay, note that this is a little strange in the way they present this. So let me, first time I looked at it, I was super confused. Okay, so here's our shift table. Okay, so in this instance, we have A through Z, we have an underscore. Okay, that's all that we have. Okay, so when we're looking at the pattern, okay, so we're looking for barber. Okay, so A appears one time in there. Okay, and because of at this position, we can move it over 4. The B is in this position, we can move it over 2. Okay, the C doesn't exist. If it doesn't exist, remember we can go the whole 6. That's the length of the pattern. Okay, so in fact, for every letter that doesn't exist, the dots here, everything from F to R, we don't care about. Okay, because they're all 6. Same thing from R to Z. Same for the underscore. They're not in the pattern. Okay, but we're looking for this last one here. So this B is a 1, 2. The A is a 1, 2, 3, 4. Okay, we have the E is just 1 to the end, so we only have an E there. Okay, and then the R, since we're testing for this one at the end, we know that's already going to be okay. So when you look at the other R, would be 1, 2, 3. So it's a 3. Okay, so again, this is the text we're searching for, with barber being the text. The first thing we do is here, we line up with this A. We look up here and see that we can move 4. Okay, we move it 4, so this A lines up. Okay, so now we're here, we look here, there's an E. Okay, E is a 1. Okay, so we move it over 1. Okay, so now we're here. Okay, we now have this R lined up against the underscore. Okay, underscore is a 6. Okay, so rather than going down the page, at this point it goes back up to here. Okay, so now we're here. Okay, we can move the whole 6 to there. Now we have the R lined up with a B. We look up a B, we can go 2. Okay, so here's where it's moved to 2. Okay, we now have the R up against an R. Okay, R is a 3. We move it 3 characters for here. And it turns out we now have found the pattern we're looking for. Okay, so the worst case efficiency of this is going to be big O of NM. Okay, but so I mean, it's not bad, could be worse. Okay, so all of that was Horseball. So the Boyer Moore is going to get a little more complicated. Okay, it has a bad symbol shift, it has the good suffix shift, all that stuff. Okay, and again, you can read through this, but I'm not going to test you on it. I think knowing the Horseball gives you enough of a flavor of what it is we're trying to do. Okay, nothing wrong with this. This is a fine algorithm, and you can certainly go through that. Okay, but I won't give you homework on it. Okay, but again, it's based on the other. Okay, some homework there. Okay. So the next thing's hashing. Hopefully you saw hashing in data structures. Okay, if not, we'll talk a little about here. So hashing is a way that we want to be able to have a function to take input and figure out where it should be stored in a hash table. Okay, so it says here it's an efficient way to implement dictionaries. Okay, so dictionaries again are associative arrays that are indexed not by number but by some character set. Okay, so the idea here is that you're going to create a key based on your hash function. So you have some entry. If you're storing names, you have a set of characters. You then, or if you have a number, that's the key. That's what sorry, it's not the key. That's what you're storing. Okay, you're going to put the value through the hash function. Well, I'm sorry, the key is the key is what you're trying to store. Okay, you're storing the key. So Bob could be your key, 25 could be your key, whatever it is. Okay. You send it through the hash function, which will return an integer between 1 and m-1 for a hash table of m. Think of a hash table as an array, the easiest way to do that. Okay. It will then return, each key returns its own hash address. Okay. And we usually do this on, say, modulo. Okay. Like if you have 25 is the length of your well, I'm gonna have to pop up my unfortunate, do some drawing with the mouse here. Okay. So let's keep it a simpler example, so I don't have to draw all that much, because you don't want me to draw a lot with this. Okay. If we have a hash table size, or HT size is equal to, let's say, 6. Okay. Our hash table is going to have 1, 2, 3, 4, 5. Is that right? 1, 2, 3, 4, 5. 2, 3, 4. Yeah, that's ugly, but it's too big. But let's see. We've done that one first. No, I want to draw 1, 2, 3, 4, 5, 6. There we go. Ugly as it is, that is basically what we're talking about here. Okay, so this is our hash table. Okay, and we want to store, let's say, integers in this hash table. Okay, so the values for this, that should be a 0, 1, 2, 3, 4, and 5. Okay, and say we're going to store integers in this hash table. Okay, what we commonly do for a hash function, if you want to have a function, okay, so our hash function that's going to take some key, which is an integer, and it's going to return from 0 to 5. Okay, we can do this with the modulo operator of 6. Okay, so that's what our function will do. Our function will just return k, which is an int, mod 6. Okay, so the way mod works, remember, it's a remainder and a division. It can't be anything but 0 through 5, right? If the number is evenly divisible by 6, so if it's 6 or 12, 18, whatever, the remainder is 0. Okay, if it were 7, the remainder is 1. If it's 8, the remainder is 2. If it's 9, the remainder is 3, and so forth, all the way up to a remainder of 5. Okay, 11 would have a remainder of 5. Okay, but if you add 1 to that, and so if there were a remainder of 6, like 12 would be the next one in the sequence. Well, 12 has a remainder of 0, because at that point you have another whole version of the number to be able to get a number whole of the divisor. Okay, so that should work in this case. Okay, so again, whatever number you have. So let's say I want to store an 11. Okay, my key is equal to 11. Okay, my that's an h function of 11. Okay, so if I take 11 and do a mod 6, okay, so it's going to be an 11 mod 6, which equals 5. Okay, so that means I would store an 11 right here. Okay, and then let's say I want to do a k is equal to 62. Keep it easy. Okay, so my h fun of 62 is going to be equal to 62 mod 6. So I take 62 divided by 6, gives me a remainder of 2. Okay, so 62 would be stored there. Okay, so that's the basic way this works. Okay, so we have some issues here, especially with a hash table this small. Okay, in that, what if I wanted to store 8? Okay, so my k is now equal to 8. okay, then my H fun of 8 is going to be that 8 mod 6, which also equals 2, okay? We can't store anything else there because there's already something there, okay? I guess before I talk more about that, the way this would work in searching, okay? So let's say you want to search, okay? You're going to search. It's really ugly. Wish I had a better mouse. Wish I was more skilled. If we're going to search, let's say for a 63, okay? I then do my H fun of 63, which is going to give me that 63 mod 6, which is going to give me the remainder, or the hash index of 3, okay? I look to see, is there anything at 3, and is it 63? It's not, so I know I don't find it, okay? So once you have this set up, you can find out if something's there the very first time, okay? Unless you have issues. We'll talk about the issues next, okay? So again, let's go back to what we just did down at the bottom here, okay, with this idea of a collision. So in this case, we've already put a 62 into our hash table. We're now going to try to put in an 8. They have the same remainder, okay? We have options here, okay? And the first option here is to, when we try to store it here and it's full, we're just going to move it 1 to the right, okay? So we're going to put an 8 right here, okay? And this is called, I think, I have to read it again out of the book. I've got the book hidden now. I might be able to get it. Let me see. Yeah, so it's called closed hashing, but open addressing, when you always keep things in the hash as long as you can, okay? But it means if I'm searching for something, okay, again, I'm searching for 122, okay, which also has a mod of 2, okay? I would have to search there, but because it may be next door, I would have to keep searching until I hit this blank space, okay? So it increases your search time here, okay? And it's also the case that if I wanted to store something now, if I wanted to store a 63, for example, I can't put it here, that's already filled, I have to put it here, okay? And now if I'm searching for something that goes to a 2, I'd have to search all the way to the end, okay? So it certainly becomes a problem, okay? And hash tables are much bigger than 6, so usually you have more room, so it may not be as much of a problem, okay? Now, any number that we give, as big as you want to get it, always has a mod 6 value between 0 and 5, okay? So keep that in mind, okay? But the other way we can do this that oftentimes makes sense is called open hashing. And it's where each hash, it's basically a hash of linked lists. Okay, so however you choose to draw linked lists. So if you had a 62 here, and then you get a 2, or an 8 was what we did before, you would have an 8 here, okay? And you can keep going, you know, until you get the end. So the advantage of doing it this way is that there's no limit except the system limit of the computer, okay? The memory limit of the computer, okay? So which shouldn't come into play, okay? So for a hash table that has no collisions, you can get your search results immediately. Either it's there or it's not, okay? If you're using the open hashing, okay, where you stay, sorry, the closed hashing, where you stay inside, the first one we did, okay, it means that the worst case scenario, you may have to search your longest length without a space in your hash table, okay, the longest consecutive values with no break, okay, where with a linked list implementation, okay, or the open hashing, okay, the worst case scenario is the length of the longest linked list, okay, you may have to search through all those to find it, okay. So again, if I were searching for 20, which also has the value of 2 for its index value, I would have to search 62, nope, 8, nope, it's not there. Okay, now we're done. Okay. So hopefully that makes some sense. Let's go back to the text here. And again, sorry, my drawings were bad. Okay. So again, here we have our hash table. We have the hash function. We have the hash. I called it a hash index with the hash address. Okay. So we have the open hashing again, also called separate chaining, which uses linked list. Okay. Then we have the closed hashing, also called open addressing, which just is confusing. Okay. So in this example, we're going to do the open hashing, separate chaining, okay, for the list of words, a fool and his money are soon parted, okay. The hash function this time, we're going to use a function of add the positions of the word's letters in the alphabet, and then compute the sum's remainder after division by 13. Okay, so A is a 1, B is a 2, and so forth. Okay, add those together, divide it, or divide by 13 and return the remainder. So we're going to have from 0 to 12, what you see at the bottom here. Okay, so if you go through and calculate, the hash value of A is equal to 1. A is a 1. 1 mod 13 is 1. Okay. The second key, fool, we're going to add 6, which is the F is a 6th letter, 2 15s because O is a 15th letter, plus a 12 because L is the 12th letter. Add those together, mod 13 is going to give us a value of 9. Okay. So when we go to store this, we get the following table here with the hash addresses and the keys. Okay. We're all okay here. They're all separate, except the R and soon both go to 11. So in that case, we just have another element in our linked list. So worst case scenario, you'd have to search for 2 things. Okay. So that's a good example of that. There's some metrics there, looking at the load factor, which I'm not particularly interested in. Okay. So what I was telling you as far as on the closed hashing, where you're going to keep it all in the table, if you want to move one to the right, okay, the simple moving one to the right is called a linear probing. There's other, you can do a quadratic where you're doing it 1 the first time and then 2 and then 4 and so forth. But this one's a simple enough to give us an example here. Okay. So in this case, we have the same table as before, but when we go to store the soon, we see that 11 is already filled with R. Okay. So we have to put the soon in 12. Okay. So then when parted really goes to 12, it has to be put back over here at 0. Okay. So we assume a circular thing here with the linear probing. Okay. So it means that now the biggest string without a break is 1, 2, 3, 4, 5. So if you're searching for something that goes that has a hash value of 9, you may have to go 5 searches, okay, before you know for sure that it's not there. Okay. So I think that's relatively straightforward. Hopefully that's okay. If you have questions, let me know on Thursday. Okay. And then we're to the last section on B trees. Okay. Again, B trees, we're not going to get super involved, but it's just, it's a pretty important technique. Okay. So again, you may have gotten to this in data structures, maybe not. I don't know how far you got, but in a B tree, B is not a binary tree in that case. Okay. But it is going to be a tree that we're going to use as an index. Okay. So an example here, if you're going to make, if you're old enough, and some of you are, to remember encyclopedias, okay, you're not going to have one volume with all possible entries, okay? Instead, you're going to have multiple volumes. And to keep it simple, let's say you're going to have a volume for each letter of the alphabet, okay? So that's the idea of an index, okay? So that's how the B tree works here, okay? So the B tree is used a lot, databases, all kinds of things like that, okay? So the B tree size will determine how many children it can have, okay? And the way these diagrams work, this is the B tree of order 4, okay? So you could have one link off of this one link from there, one link there, and one link there, okay? So we have 4 possible ways out of each node, okay? And then we have values stored there, okay? Such that there is, the B does have somewhat of a binary element, in that everything to the left Okay, there aren't just two children, but everything to the left of any node or any position here, okay, is going to be smaller than that. Okay, so in this example, the 20 is the first thing that we had. Okay, it has to be the smallest in this node. The 51 has to be to the right. Okay, this 20, the link here from the edge are things that are less than 20. Okay, so this node we have an 11 and we have a 15. Okay, so the 11 and the 15 are also, these again are not leaf nodes. The leaf nodes just have up to 3 things with no other things going out of it. Okay, so this has an 11 and a 15. Again, the 11 has to be smallest. We have something on this one. Okay, so the links here are as follows. This first little, the narrower rectangle are things that are less than 11. So the 4, 7, and 10 are all less than 11. This next link are for things that are between 11 and 15. Okay, and everything has to appear here at some point. Okay, everything is stored in the leaves. Okay, so even though they appear here. So the 11 and the 14 are both between 11 and 15. Again, like in Python, including 11, not including 15. Okay, this one are things that are greater than 15 because we're not using the other part. Okay, the 15, 16, and 19 are all greater than 15. Okay, for this one is between 20 and 51. Okay, so we have another node here, which we have 25, 34, and 40. So this is things that are, again, these all are greater than or equal to 20. Okay, so 20 can be here. But in particular, they're also less than 25. So they're between 20 and 24. So 20 and 24 are here. This next one, again, they have to be, it's greater than 25, greater than or equal to 25, sorry, and less than 34. So these are here. This one's going to be greater than or equal to 34 and less than 40. The last one here is greater than 40, okay, but less than the 51 because that was the bound from up here, okay. And then from this one, there are things that are greater than 51. Go over here. There's only one here. This is less than 60, but greater than 51, greater than or equal to 51. So 51 and 55 are there, and this is greater than 60, okay, and no limit on that. So this is the B tree of order 4. The order 4, it can have 4 children. So therefore, it can only have 3 data elements that it stores. Okay, and there's some more stuff there that we can talk about adding and subtracting to them, but that it can get a little hairy sometimes. Okay, sometimes it's pretty straightforward. Okay, it does show an example here. It starts with the tree up here in 7-8. Okay, so this is where the tree that we're at here, top of the page, and we're going to insert a 65, okay? And it shows the result here, okay? And with any luck, it doesn't break anything, but sometimes it does. There's room here, so it should be okay, okay? So when we go here, looking for a 65, okay? 65 is greater than 51. It's greater than or equal to 51. So we go to here, okay? And then here we have the things that are less than 60, the things that are greater, less than or equal to 60, sorry, less than 60, greater than or equal to 60, okay? They're always less than or equal to 51, okay? So the 65 is going to need to go here, okay? But we can't do that because that makes it too full. We're not going to add another layer, okay? So instead, what we're going to do, we're going to move up the index, okay? We're going to have a 60 here. We're also going to add a new index here to balance things out, okay? And when you look at what you have here, and there are algorithmic ways to figure this out, okay? We're going to take this middle value, okay, and promote it up to give us more space, okay? So we now have a 60 and a 68. So we have the things that are less than or equal to 51, sorry, greater than or equal to 51, less than 60, okay? We have things here that are greater than or equal to 60, but less than 68. 68 is going to be over there, okay? And then finally, the last part is going to be greater than 68. Okay, when we do that, we now have the 68. This points to the 60 and the 65, and the 68 and the 90 are there. 68 and 80, sorry, are there, okay? So if you're adding these, again, we still have some more room. We're not full, Okay, we can still get, let's see, these are full. One more can go here, one more can go here, one more here, one more here, one more here. Plus we have a whole other branches here, and another branch here, another branch here. So we can store more there for sure. Okay, so we don't need to add a whole new level at this point. Okay, so that's the B trees. Okay, so won't go into a whole bunch of detail on that, but these are things that are worth knowing something about. Okay, so that's it for the video this week. So again, it's a short turnaround time to our meeting on Thursday because of the exam, but hopefully you'll be able to take a look at this before that meeting. And I will post some homework later today. Okay.